before we move on with the limit concept or strategy, well, that looks wonderful. Not sure what just happened there, but before we move on, there, that looks better. I must hit the wrong one. We have to review a little bit possible discontinuities. Some of them are removable, some of them are not. The ones that are not removable, we very cleverly call non-removable discontinuities. Okay? Again, discontinuous means kind of, in general, for now, we're going to call it as if you were to make the graph, you couldn't complete the graph without picking up your pencil when you were drawing it. Okay? That's what a discontinuity is, something that makes you pick up your pencil. So the non-removable are normally referred to just as asymptotes. Okay? There are actually three types of asymptotes, if you remember from advanced math. We're going to at least talk about these two today, which are the vertical asymptotes and the horizontal asymptotes. Normally, remember, we only really have to worry about these when it's a rational function. In our one-parent graph, that's a rational function, is that one, correct? Because there's a variable in the denominator. Okay, that's rational. So to find vertical asymptotes, we basically have to set the denominator equal to 0. Why? What does that tell us? In general, who can kind of in words say what that actually tells us? Don't everybody answer at once. Values that will make the function undefined, right? Or in other words, if I put 0 in this particular denominator right here, it's dividing by 0, right? That's a big problem. Or another way of putting it, it tells us the values that are not in the domain, right, of this particular function. So for example, 0 is not in the domain of this particular function we're looking at here. And when you have that, that is a vertical asymptote, because as you're graphing it, like the graph of this one has an asymptote there and there, and does that, right? So you can see it tells you the value that's not in the domain. Okay? And really it ends up being x equals 0, which of course is a vertical line anyways. Okay? So for horizontal asymptotes, I've given you two tricks. There is actually to actually do horizontal asymptotes is a way more work than these two little tricks. Okay. The first one that you could possibly have a horizontal is if the numerator and denominator have the same degree. Then all you have to do is just kind of look at the fraction. And what I mean by that is if we have y equals x squared plus 1, to have the same degree, what has to be the degree on the bottom is x squared, right? So, but maybe you have 3x squared minus 7, all right? Do you agree they have the same degree? Yep. Once they have the same degree, who really cares about that one? Who really cares about that one? You look at this fraction right here, which is 1 over 3. Y equals 1/3 is going to be your horizontal asymptote, okay? And we'll discuss why once we look at a few examples, okay? Because that would be a wonderful question at this point. Why does it end up being that, okay? And if the denominator has a higher degree than the horizontal asymptote is automatically y equals 0. Here is a good example of that. Okay, y equals 0 on that one. Again, once we do a few examples, either I will see if you can tell me why these two work, why these two shortcuts work, or we'll have to discuss it. Okay, any other questions at this point? Okay. So let's determine the asymptotes for this particular function here. Well, is it a rational function? Yes, we have a variable in the denominator, so yes it is. So look for the numbers that would make the denominator 0. Again, we're really looking for numbers that are not in the domain. So the simplest thing to do is actually just set the denominator equal to 0. And I think I can probably skip some of the algebra on this one, correct? I think most of you can see how to do the algebra in your head. Add the 1, divide by 2, right? So in other words, it's x equals 1/2, right? So look back up there. If I put 1/2 back into that equation up there, do I get a result? Is there something that comes out of it? No, because once I put 2 times 1/2, I get 1. 1 minus 1 is 0. 1/2 divided by 0 is undefined, right? No result comes out. So in other words, 1/2 is not in the domain. Okay? I don't know if it's on here or not, but we'll try. Whoops. There it is. X equals 1/2. That's what that graph of that equation looks like. X equals 1/2. Okay. Now, in the actual graph of this thing, the asymptote doesn't really count. That's kind of like a guideline for us. That's why we make it dashed. We're just using it as a guideline. Okay? Because I know no matter what, I'm not going to be allowed to put in 1/2, so there wouldn't be a result there. So I better not actually have one. And how about step 2? Which shortcut should we use? A or B based on your notes from earlier? Is it the degree the same, or is the bottom bigger? Use A. Why is that? Because, yeah, the degrees are the same. So we're looking at basically y equals x over 2x minus 1 is what we're looking at. Agreed? And so the reason let's look at this particular one. Horizontal asymptotes are obviously the ones that go kind of across your graph from left to right. And so what we're really looking for is x gets really big in either direction, a really big positive or really way far negative, right? And so in other words, let's make x really big, like 1 million, right? So that x also has to be 1 million. So it's really 1 million over 2 million minus 1, right? Does that minus 1 really have a whole lot of power in what's going on here once x gets big? Not really. It doesn't have a whole lot of power at all. So in other words, it's really just 1 million over 2 million, pretty much, right? Okay. So do you see how that's why we just look at that fraction? Because wouldn't 1 million over 2 million pretty much simplify to 1/2? Right? And so again, this is as x gets big. Okay, this is what's happening to them. So notice this one's also 1/2. Do you think they always just match? No, they don't always just match. Okay, so y equals 1/2 is then a horizontal one going that way. Okay. Now the one thing tricky about horizontals is the horizontal asymptotes will hold true as x gets way far out in both directions. So as x gets out that way or as x gets out this way, it will get pulled to that asymptote. But remember from advanced math, it is possible for horizontals to misbehave every once in a while. It can actually cross the horizontal, but it does come back to it. It cannot cross vertical. Okay. So we take a look. We have determined the asymptotes. So why don't we just take a look at the sketch of this particular one. I don't believe this one misbehaves. I think this one's pretty good. I would love to have my graphing calculator back, but I don't have it at the moment. I believe this one pretty much just does that and that. So you notice over here, as x got big, it kind of got pulled to that asymptote. Okay. Questions on that one? And if we had to do it by hand to find out where it was going, we could always just start substituting in some x values, make an xy table, find out where it's going if we had to do it by hand, right? Questions on that one? All right. Well, why don't you take some time then and determine the asymptotes for this one if there are no questions. Go ahead. I'll pause the video again. If you're listening to the video, actually pause it. Don't just wait for the answers to pop up. Well, let's take a look. So you're probably used to me by now. Normally if I ask, are there any questions, you probably should have had a question, right? And this falls right into that category. So look for numbers that would make the denominator 0 is what it says here for step 1. And again, it's a rational function, so we would set x squared plus 2 equal to 0. Again, I think we would concede that the algebra would lead to x squared equaling -2, right? And then it would lead to the square root of -2. Or positive and negative square root of -2, technically, right? But that's an imaginary number, correct? So as far as real numbers are concerned, are real numbers all in the domain of this function? Am I allowed to plug in all real numbers? Yes, because the only number I'm not allowed to plug in is imaginary. So that means I can plug in any real number I want. So as far as vertical asymptotes, there aren't any. Okay. Again, that's the empty set, meaning there are no answers in that solution set. So there's no vertical asymptote. Which shortcut? Now that doesn't mean there's not a horizontal. So let's look for a horizontal. And again, what would you do there? Which shortcut would we use this time? B, because the bottom is bigger. So let's talk about that one. So it's really kind of saying y would equal this. Again, what are we, with horizontals, we're worrying as x gets what? Bigger, either way positive or way negative, right? So let's use that million number. I put 1,000,000 in here. So the top is 1,000,001, correct? I put 1,000,000 in there. 1,000,000 squared. Well, that's considerably larger than 1,000,000, isn't it? So the +1 and the +2, are they really having a whole lot of influence once x gets large? Not really, does it? These don't have a whole lot of influence on the problem. One of the terms you may hear for that is called negligible. Okay? So it's 1,000,000 over 1,000,000 squared. And do you believe as x gets larger, what happens to the disparity between the numerator and denominator? In other words, does the gap get bigger or smaller between the two numbers? It gets bigger, right? So if I go to a billion over a billion squared, the difference between those two numbers gets huge, correct? So it's a big number over a ridiculously large number, and it just gets worse. So as x gets larger, what actually happens to this fraction? It actually gets smaller, correct? Okay? It gets very, very small, almost to the point that we can't even see it. And what does your little rule tell you for this one? If the bottom is bigger, by default, it is y equals 0, because as this gets further out, it's going to keep getting worse, right? There's not much I can do about it. So we know y equals 0 is an asymptote. So how does this work then? How can I possibly get a graph when I have an asymptote like that? There's no vertical. How does that work? Okay. This is one of those cases where it does break the horizontal. You could start substituting in some points. I have a few of them here. But what actually happens, and I could figure out exactly where it happens, but I have it like this. It goes up like that and comes back. It actually crosses over and then comes back. So as x gets big way far over here, it comes back to the asymptote. It gets pulled back in. And over here, as x gets really, really negative, it gets pulled back in. Okay? But it is actually allowed to cross it sometimes. Of course, if we had the graphing calculators handy, we would get a much more accurate graph than that. And if you're wondering why there's kind of some humps kind of in the middle there, well, think of the opposite. What if x gets really, really small? As x gets small over small squared, when you take something small and square it, like something less than 1, so for example, a half, and you square it, it actually gets smaller. It becomes a quarter, correct? Okay, so the numerator stays big, the bottom actually gets smaller, so the overall result gets larger. Oh my goodness. All this math and numbers, I tell you. Okay. Who came up with this stuff? All right. What's that? Yeah, I know. All right. What do we think about this one? Determine the asymptotes, then sketch the graph. I don't know why that one's so much bigger than the rest of them, but must be. Yeah. All right. Well, I'm taking a look at this, and we haven't talked about finding holes yet, and so we're not going to worry about holes right now. But I'm not going to worry about a hole either because I do not believe the numerator is factorable. Okay, multiply to be 21 and add to be 2. I don't see that working out so good in real numbers or in rational numbers. But I do believe the denominator does. So let's find our verticals, or our numbers that are not going to be very good in the domain. Okay? So in other words, we need to factor, or hopefully this factors. So it has to multiply to be -3 and add to be -2. I do believe such numbers exist, and they are actually real this time. And rational, pretty sure. What are those numbers? Anybody? -3 and +1? Is everybody okay seeing there's a 1 out front that we skip the... Just do the real shortcut for the factoring, right? Okay. The factors then are basically x -3 and x + 1. Those are the actual factors. That's the shortcut. And then you could set them each equal to 0 to solve, but that's not what we're going to try and do right now. The reason we're not trying to do that is because that's really what my denominator is. That's my new denominator, and as you can see, it would, if you actually kind of FOIL that out in your head, you do see that you actually get back to it. Does that really cross with anything in the numerator? Nope, because that didn't factor. Okay. So that is my denominator. So what will actually make that say 0? When x is what two values? When x is 3 from this one right here, and when x is -1 from that one right there. Well, I think it's there. There it is. And there it is. So there are some verticals. Any questions on how I found those? No? Just in a second I'm going to erase that stuff. So everybody good? Got it written down? So now that we found that, what's probably something we should find next? horizontals. And so we take a look. Now remember, horizontals, we're really concerned about what happens when x gets big, or as x goes out way far into the positives and way far into the negatives. So again, you're putting in a huge number here for x, that same huge number there, same huge number there, and same huge number there. So once again, the +7 and the -3, do they have a whole lot of influence when x gets ridiculously large? No. And when all is said and done, how about the 2x and -2x, really? If you take 1,000,000 and square it, and then plus 2 times infinity, or 2 times 1,000,000, really that's not as helpful. So the most powerful terms here are the ones with highest degree, correct? And so what I told you to do, and this is, which shortcut are you using here, is you're using the first one, right? The powers are the same. Okay, because they are kind of going out quickly, so it's really 3 over 1, correct? And so y equals 3 is your horizontal. I will tell you right off the back, whenever you have multiple verticals, this little asymptote here definitely does not have to hold because the x values are so small, right? Once the x values get big, again, way out here and way out here, that's when that horizontal holds. Okay. Obviously, if we had to, we could choose a bunch of points, but I'm just going to kind of show you what happens on this one. This one actually behaves. Okay. This one over here on the left actually misbehaves. Comes through and then comes back. And there's no good way for me to tell you which ones are going to misbehave and which ones are not. That's where we're going to use our technology. And this one down here actually behaves. And in the middle of verticals, it's a pretty much anything goes kind of time, which is rather fitting, seeing homecomings coming up. Anything goes. Okay, any questions about asymptotes in general? Okay. The hardest part for people is the horizontals. They think that the asymptotes have to behave. The verticals do, and do you understand why they have to behave? Because they're giving us something that the result is either undefined or imaginary. So it's not even part of the domain. Here, some of these values are still part of the range. That's why it's a problem. It's just as x gets really negative and x gets really positive, they're not going to be part of the range. Okay? We good? All right. Not sure what I just did.